Okay, so today we're going to introduce trig identities. We'll have a couple days to do this. We'll do these again on Wednesday. So we'll introduce all of them today. Wednesday we'll do a lot more of examples and practice with them. So trig identities, the most important one is the Pythagorean identity. Pythagorean identity says cosine squared theta plus sine squared of theta equals 1. Where when we write things like cosine squared of theta, really what it means is compute the cosine of theta and then square it. It's not the best notation. It's kind of a shorthand notation that mathematicians have adopted, though it isn't consistent with some of the other function notation. But from now on, if you ever see an exponent in any of the trig functions, cosine cubed, cosine to the fifth, it means compute the cosine and then raise that ratio to that corresponding power. So where does this come from? It comes from Pythagorean theorem. That's why we call it Pythagorean identity. So how so? Let's take a look. If we have our triangle drawn in standard position with an angle here, theta. Cosine squared of theta is x over r squared. Sine squared of theta, we write the sine, y over r squared. And we should have this equal to 1. If we now square each of these, we will get x squared over r squared, y squared over r squared. And so we get x squared plus y squared over r squared, and that should be 1. And why is that 1? By the Pythagorean theorem. We know that x squared plus y squared is r squared. So that is our first valid identity. I'm going to put a box around it as well, because that one's an important one to remember. There's two other identities that we commonly use from this one. We call them Pythagorean identities because they are essentially derived in the same way. But you can also modify this identity to get them. So I'm going to go ahead and do that. If we actually start with this identity now, and we divide both sides by cosine squared of theta, then this is going to be cosine squared divided by cosine squared plus sine squared divided by cosine squared. The right, 1 divided by cosine squared, is just secant squared. And now simplifying these two expressions, we get 1 plus tangent squared is secant squared of theta. Likewise, if we start with our original identity again, and instead divide by sine squared on both sides, we'll get cosine squared over sine squared plus sine squared over itself. And on the right, we have a cosecant squared. And so here we'll get cotangent squared plus 1. is cosecant squared. Not sure if I can get all those on screen. Looks like we can just barely. So those are the three Pythagorean identities. The other identities we have, at least the next set, we're going to talk about even odd identities. So if you think way back, beginning of the semester, we talked about even and odd functions. It has to do with how they are reflected across the x and or y axes, and the symmetry that is involved. So sine is an odd function, meaning that if I flip it across the y-axis, flip it horizontally, it would be the same as if I took sine and flipped it vertically. Or another way you can phrase that, if we multiply that minus sign over, that if I take a sine and then flip it horizontally and then flip it vertically, we'll get back the original function. Cosine is an even function. Meaning it's symmetric horizontally across the y-axis. If I flip it horizontally, we get back the same function. And then from those two, we can actually derive the rest. So what is tangent? How do I check with tangent if it's even or odd? We stick in a minus x for the argument and then see if we can simplify it. So tangent we can write in terms of sine and cosine. And now because sine is odd, I can simplify the numerator to minus sine of x. And the denominator, cosine of minus x, is the same as cosine of x. And so all in all, we're getting a negative tangent of x. So that tells us tangent is odd. Then the other three trig are going to follow exactly the same just by taking the reciprocals. So cosecant of minus x is minus cosecant of x. Secant is, secant of minus x is still secant of x. And cotangent of minus x is minus cotangent of x. Of the ones you should definitely remember, I would say the first two. Let's put a box around these. So these are the 6 even odd identities. But for the spirit of memorizing as little as possible, I would say make sure you know these two. And then from those two, you can figure out the rest if you need to. And then the last set of identities that we're going to talk about today are called cofunction identities. Cofunction identities say that sine of pi over 2 minus theta is cosine of theta. So where does this come from? This comes from the fact that if I draw a right triangle, one of the angles is always 90 degrees. So if we have an angle theta, Well, cosine of theta is x over r. What is sine of pi over 2 minus theta? You just have to recognize that in this triangle, since the sum of all of the angles in degrees is 180 degrees, the sum of all the angles in radians is pi. So we have pi total. If one angle is pi over 2, that means the sum of the other two angles have to be pi over 2. And so this angle here is pi over 2 minus theta. And now we just take a look. Well, what is sine of this angle? It's going to be the opposite over the hypotenuse. So that one's good. And I would say if you can memorize that one, remember that one, remember where it comes from. The other ones are going to be very similar. So just as well, we could have started with cosine of pi over 2 minus theta, and that will give us sine of theta. Tangent of pi over 2 minus theta will give us cotangent of theta. And you can derive the other three by the reciprocal relationships. So for example, if we took 1 divided by this and 1 divided by the right side here, we would have cosecant of pi over 2 minus theta is equal to secant of theta. And you can derive those, or reason those out the same way we did with this first one, just by looking at the triangle and knowing that these two angles have to add to pi over 2. Any questions? All right, so let's do some practice problems. So keep these handy. Try to explain as we go through and as we do these, give you guys some pointers as to how I'm thinking about it, what I see. Of course, it's much easier for me. This is kind of my job, so I kind of see all the steps. So I want to try to give you guys some pointers as to how you can develop that a little bit and what you can look for yourselves. So our first example, we want to simplify. Let's see, we've got sine cubed of minus theta over sine cubed theta minus sine theta. So what do we want to look for? First thing you want to look for is, are all the arguments the same? And in this case, they're not. One of the arguments is minus theta, whereas the other ones are just theta. So always try to convert all of your arguments to just theta when you want to simplify it. So our first step, what we're going to do is I'm going to write the numerator in a little bit more correct fashion to remind ourselves that that cubed is outside of the sign. We want to compute the sign first, then cube it. And having those parentheses helps us because now working inside the parentheses, we can use our even odd identities to change the argument since there's a minus theta on the inside. Sine of minus theta is negative sine of theta. And since I wrote this parentheses around it, we see that this minus 1 will actually get cubed. So always be mindful of that. If it's a degree 2, it'll affect that. Degree 5, whatever the degree is now going to affect that minus sign. So we'll have minus 1 cubed and sine cubed. And so the numerator just ends up being minus sine cubed. So now what do we want to look for? All the arguments are the same. It's a good first step. Other things you want to look for are what are the degrees of each of the trig functions. Here we have some degree 3. So degree 2s are nice because degree 2 trig, we can make use of the Pythagorean identities. All those 3 that we derived all they relate the square of trig functions. So with a cube, there's a squared term kind of hidden in there. So maybe those will come into play. The other thing you want to look for are the sheer number, the diversity of functions that are appearing, the number of unique functions, we should say. And in this case, it's not an issue. Everything's in terms of sine. So if everything's in terms of sine, let's go ahead and keep it because that helps us do some factoring and simplification. It is a step that if we have a lot of different functions, sometimes it helps to convert everything into sines and cosines and then work from there. So since we have all sines, let's try to see if we can factor something because we do have a quotient here. And you notice that in the denominator, we at least have one factor of sine. I'm going to actually factor out a minus sign just so we can get rid of that minus sign in the numerator. So when I factor out a minus sign from the denominator, the sine cubed will be a minus sine squared, and the minus sign will just be 1. So always remember when you're factoring out a minus sign from a difference, just flips the terms. And we can divide those two. And what are we left with? We're left with sine squared theta over 1 minus sine squared theta. So we're a little bit closer now. We've reduced a lot of these degrees, and now we have these degree 2 terms. So we can make use of these Pythagorean identities. And there's not much else we can do since I can't factor anymore. We could factor this as a difference of squares, 1 plus sine theta times the quantity 1 minus sine theta. However, those aren't appearing in the numerator. So sometimes you'll have to use that trick, but in this case, probably not going to be fruitful because nothing else is going to cancel. Instead, let's take a look at what another useful fact about these Pythagorean identities. So another thing they do is they essentially convert one trig function or the square of one trig function into another trig function. So for example, if I took this and solved for cosine squared, just subtract that sine over, tells us that 1 minus sine squared is a cosine squared. And that's nicer in some sense. We are changing the function. We're converting sines to cosines. However, the other thing that these Pythagorean identities do is that they'll convert a sum or a difference of maybe a constant and another trig function into just a single trig function. So it's getting rid of that difference for us, which can make our lives a lot easier afterwards. And so when we do that, we'll have sine squared theta over cosine squared theta. And that's just going to simplify to tangent squared of theta. Any questions? All right, let's do one more. So it says show cosine x over tangent of x plus sine of x is equal to cosecant x. So anytime the problem just says to show, you want to start with the one side, usually the more complicated side, and then try to simplify it down to the right. It's essentially the same process as we just did, except they give us the answer ahead of time. They give us what we should be able to get by simplifying this expression on the left. So I'm going to start with what we have on the left. And one thing to notice is that there's a lot of different trig functions that are appearing. Not only is there sines and cosines, we also have tangents, and then we're supposed to end up with a cosecant. So a lot of different trig functions appearing there. And if we go through our other checklist, we don't have any squareds. So Pythagorean identity is not going to be useful at this point. And all of the arguments are the same. So no minus signs in the arguments, no pi over 2 minus. So the cofunction identity and even and odd, not going to be useful at this point. Pretty much the only thing we can do is perhaps start with this tangent. Sine and cosine, as I've mentioned, are like the building blocks. So when in doubt, you can almost convert any trig expression down to sines and cosines. And sometimes that's helpful for seeing what comes next. So let's go ahead and convert that tangent. And now we are dividing by a fraction. So it's the same as multiplying by the reciprocal. And now when we combine our terms, we see we have a cosine squared in the numerator. Sorry, just one sine in the denominator. And this plus sine x is still hanging out on the outside. So less diversity here, usually a little bit better. Less things you gotta know, less identities you gotta know. Now we want to take a look, try to find an identity that relates sine and cosine. And namely, since we have cosines, 2 powers of cosine, we can use our Pythagorean identity again. And this time we're kind of using it in the opposite way. In the last example we saw, we were using it to simplify a sum and difference and get one expression. In this case, it might be helpful to convert everything into sines. And why is that? Because, well, we know the result, we should get a cosecant. And what is cosecant? Cosecant is 1 divided by sine. So this is really like a sine as well, but in the denominator. And if we look at what we already have a sine in the denominator. We've got a sine hanging out and then something else going on in the numerator as well. Maybe if we convert everything into sines, it'll help us out a little bit. So I'm going to go ahead and convert those cosines to 1 minus sine squared. Again, just using the Pythagorean identity and solving for cosine squared. If you're not used to using these or don't have them memorized yet, practice writing these out. The more you write it out, it helps ingrain it in your brain. So we converted our cosines into sines and some constants. And now we're getting closer. Everything's in terms of sines. We got to end up with a cosecant. So we have a sine in the denominator. So tips for now, simplifying fractions. Factor if you can and divide. But again, This will factor into a difference of squares, but the denominator is already as factored as it can get. And so it's not going to cancel a 1 plus sign or a 1 minus sign. The other thing we can do, though, is since I have a sum outside of the fraction, it's probably not a bad idea to split this fraction into a sum of two different terms. So you're already adding these kind of straggler terms outside of this fraction. Let's just see what it looks like if I split everything up term by term with addition and subtraction. And now this helps us a little bit because this term I can simplify. We have sine squared over sine, so one of those powers of sine are going to divide. And then I'm left with 1 divided by sine of x minus sine of x plus sine of x. So minus sine x plus sine x, that'll just be 0. And we are left with 1 over sine of x or cosecant of x. I guess since it's an identity, put a little check mark indicating that we got what we were supposed to. Any questions?